Hello, everyone. My name is Charlotte Snow. I spent my summer at the National High Magnetic Field Laboratory working under Dr. Kaya Wei and her group. My project, Site Selective Substitution in RT2 Zinc 20, Effects of RT and Dual Site Disorder, aim to enhance the low temperature thermoelectric performance of 1,2,20 compounds through targeted chemical doping for applications in clean energy and advancing scientific instrumentation. So, sorry. So 1,2,20 compounds get their name from their chemical composition. They're made of one rare earth unit, two transition metal units, and 20 cage units, which in our case is zinc. And they have shown great promise as low temperature thermoelectrics, meaning they can convert heat into electricity at very cold temperatures. This is especially important for real world systems that operate near absolute zero, like spacecraft, quantum computing, and superconducting magnets. And we evaluate how well these materials perform in those conditions using a number called ZT, which measures thermoelectric efficiency based on three key properties. There's high electrical conductivity, low thermal conductivity, and a strong Seebeck effect, which basically is how well that material turns heat into voltage. Our goal this summer was to improve ZT at low temperatures by tuning the chemistry of RT2 zinc 20 compounds. So to test our idea, we introduced controlled chemical substitutions at different atomic sites on the RT2 zinc 20 structure, on the R or rare earth metal site, the T or transition metal site, and in one case, both at the same time. We wanted to see how disrupting the crystal's chemical order would affect its properties like we've seen in past research. I synthesized three new compounds using zinc flux growth, a method where the elements are dissolved in molten zinc and then slowly cooled to form high quality crystals. I made one rare earth compound using ytterbium, praseodymium, cerium, samarium, and lutetium, one transition metal compound using cobalt, nickel, iron, iridium, and rhodium, and one 11-element crystal that combined both rare earth and transition metal disorder at the same time. After synthesis, we verified our compositions using energy dispersive spectroscopy, or EDS, and then we performed thermal transport measurements using the physical property measurement system. So our EDS results showed a somewhat even distribution of elements across samples, which possibly contributed to their difference in performance. But when we measured thermoelectric performance, we saw something really interesting. There was actually a large difference in what temperature yielded the best ZT score between the R and T site samples. Specifically, the T site sample did better at lower temperatures, while the R site sample did better at higher temperatures. And this temperature-dependent behavior is likely influenced by elements like cerium and ytterbium, whose electrical properties, as we've seen in past studies, change in distinct ways as temperature varies. So even though all our samples were based on the same crystal structure, the specific mix of elements had a big impact on where and how well each material worked. And that's what makes these systems so exciting. Not only are they new, but they're tunable. And that's exactly what we wanted to explore with this project this summer. So to conclude, we've created a completely new series of 1,2,20s that show temperature tunability, meaning we can adjust which elements go where to optimize them for either high or low temperature settings. As a next step, we'll study our samples using X-ray diffraction, take magnetic and heat capacity measurements, and we'll synthesize praseodymium and lutetium-based parent compounds, and we'll also investigate more R and T site combinations to improve upon our design. Ultimately, our goal is still to help develop better low temperature thermoelectrics, the kind of materials that could one day power countless high-tech systems using their properties to turn wasted heat into usable energy. There is still so much more to explore here, and I am so excited to continue my work with Dr. Wei following this summer. I'm incredibly grateful for this experience. Thank you to Dr. Wei, Benny Shundelmir, Mahak, and Dr. Lucas Nelson. And thank you all so much for listening.